you all for coming out. You're at the Institute for Astronomy. A lot of what we do is astronomy, solar physics, studies of everything above the atmosphere. The most important force in the universe is gravity. And of course, we wouldn't be able to do all those things if we didn't have gravity. It really is a great pleasure to have Garrett Lisi here to talk to us about gravity. Yes. Garrett is quite as I Googled him on the web, a web phenomenon. It was interesting reading. He got his undergraduate degree from UCLA, got his PhD from UC San Diego, and since 1999 has been, I think, a true example of an independent researcher. He has decided to devote himself to what appear to be studies of field theories and gravity in particular. Gravity is a subject which I cut my teeth on years ago also. Some of you may know that gravity is one of the most mysterious forces in the universe. It's something that connects everything to everything, unlike any other force. And we know for a fact that our understanding of gravity is fundamentally incomplete. There may be a lack of understanding of gravity, which is connected to what we call dark matter or dark energy, for example. So don't let them tell you that we understand dark energy or dark matter. They all may be a manifestation of our lack of understanding of just gravity. So it's very refreshing to have Garrett here to talk to us, hopefully at a level that we can all sink our teeth into about this very mysterious force that connects everything to everything in the universe, our understanding of gravity. So Garrett, take it away.
Thank you, Jeff, for that introduction, also for inviting me to speak here at the Institute for Astronomy. It's a great pleasure to be able to speak on my home turf of Maui for a change. And thank you all for coming. I see a lot of familiar faces in the audience, which is great. Also unusual for me giving a talk. But so today I'm going to be talking a lot about gravity and also a lot about particle physics, and more specifically about a unified geometric framework for describing both of them together. And this did emerge over about 10 years of research driven by a specific question in physics that I've been working on. And it ended up being unusually successful, this idea. But today I want to talk about mostly purely conventional description, although perhaps surprising and new to a lot of people, of a geometric description of particle physics and gravity that all works together and that also leads into some new ideas about unification. So, as far as we know, on the fundamental scales of the universe, down at the tiny scales of elementary particles, our universe is a sort of foaming quantum froth of interacting elementary particles whizzing about and interacting with one another via four forces: the electromagnetic force, the weak force, the strong force, and gravity. And from gravity, we know something very interesting. As from looking not at the small scales of interacting elementary particles, but looking up at the large scales of the gravitational interaction, where you have galaxies evolving and interacting. Successful at describing gravity as pure geometry. He described the motion of galaxies and planets even around our star in terms not of the usual prescription of a force with a 1/r² law of attraction, but rather he described gravity as the curvature of space-time, which is a very revolutionary concept, a very different kind of idea. And it's extraordinarily successful for describing what we see in the universe. So it's really telling us something very fundamental about the universe, which is that our universe fundamentally is geometric, and that it can be described using the mathematics of geometry. And this is an idea that very much sunk in to the general relativity community. It sunk into the people describing gravity. So all they're thinking now about gravity is geometric. And this culture is sort of separated from the culture of particle physics. And particle physicists are used to thinking of elementary particles whizzing about and not so much thinking about geometry. But really, my work largely started from trying to take this idea seriously, that the universe is fundamentally geometric, and to really define a similarly geometric description for particle physics that would match up with the geometric description of gravity. And much to my own surprise, I had some success with this. So I want to talk about first starting out with particle physics, and then develop a geometric description of particle physics, and then merge that in with gravity and show how everything fits together. So particle physics. Right now, as of a couple days ago, actually, they were on winter break. They needed the energy to heat parts of Switzerland. But right now, there's this enormous machine right now that is running protons around in opposite directions. This machine is on the Swiss-French border in Geneva. This is a particle accelerator with a ring that's 17 miles or so in circumference, with these enormous machines that are actually the largest machines ever built by man. And these enormous machines are actually built in order to detect the result of the collisions of very tiny elementary particles at distance scales much smaller than ever been seen before, which is to say higher energies that have ever been seen before. And these are absolutely enormous machines. There's these two detectors for detecting the results of these collisions are huge. There's a little picture of a human here just to give the scale of these machines. You barely even see. But so these machines, this particle collider runs protons in opposite direction around the ring. They collide the protons together at the center of one of these detectors. And then the collision results in a little burst of energy and a spray of elementary particles. And by doing this at a higher energy, where these protons are traveling very close to the speed of light, by doing this, you create all sorts of elementary particles. And by having this machine with this extraordinarily high energy, we see new particles that have potentially never been seen before. That's what we're hoping to see. And in this way, we find out what the universe is made out of at these tiny scales of elementary particles. And after having played this game with previous particle accelerators, we've been able to see a whole zoo of elementary particles. So we're familiar pretty early on with electromagnetism and certainly with gravity, which is holding everybody in their seats. But these particle accelerators, with these experiments, we've been able to find out about these new forces fairly recently. Only the second half of the 20th century did we find out about some of these other forces. Not only the force of electromagnetism, which is mediated by the photon as a quantum particle, but also the weak force and the strong nuclear force that acts inside of atomic nuclei between quarks. And for these forces, they also interact with matter, which are things like electrons and neutrinos. And the protons and the neutrons that we used to think were fundamental are actually consist of quarks, which come in various varieties. And this whole set of fermions, if you take one of them, like the electron, it comes in 8 different states, corresponding to different spin states, as well as having antiparticles, usually called positrons. So you basically have 64 elementary particles here, all interacting with these various forces. And then this pattern of 64 particles repeats 3 times. There are 2 more copies of elementary particles that normally they don't exist in normal matter, but we see them in these particle accelerators like the LHC. So we have this whole zoo of elementary particles. And there's a very nice mathematical description for how these things interact. Don't be scared. I'll show you some equations, but they'll go away and there'll be lots of pretty pictures. So these various forces interact with the matter according to what are called Lie groups. Okay, and the map looks kind of, don't worry about that. But I'll show you the pictures corresponding to these Lie groups and their structure, and that's really what this talk is largely going to be about: is understanding the structure of these Lie groups and how that corresponds to the interaction of elementary particles. So all of these forces, the gravitational force, the weak nuclear force, electromagnetism, and the strong nuclear force, correspond to different Lie groups, and they have names, and I'll get into their description. And this interacts with the matter being the gravitational frame, the Higgs field that hasn't been detected yet, but this Higgs field and its existence is the main motivation for having built the LHC. We want to figure out whether this Higgs field exists and how it acts. But we have good mathematical models for these things. But anyway, this plot here sort of shows the zoo of all known fermions that have been detected. And it's kind of a nice periodic table of particles that have been discovered. And there are a lot of them. But it's sort of a mystery as to why the universe has this structure. Okay, why this particular structure? So that's a mystery I'll try to find some answers to. But so these elementary particles all interact according to the structure of these Lie groups. And these Lie groups, what are they? They're basically nice, smooth geometric structures that are constructed by twisting sets of circles around each other. Okay, that sounds really simple, but that really is what they are. That's it's just like there are different ways of tying knots into string. There are different ways you can consistently twist circles around one another, and mathematicians figured out all the different ways you could do this consistently, and this corresponds to all the different kind of Lie groups. And these geometric shapes correspond to the interactions of these elementary particles in a very specific way that I'll describe. But I'm going to start with the simplest one, which is the force of electromagnetism and its Lie group. So just so you think that this isn't a purely weird abstract talk, I want to really sort of convince you that this is really what's going on in our universe. I mean, this room right here and the whole universe is filled with electric and magnetic fields. Okay? Every point in space-time has an electric and a magnetic field on it. Right now, just the magnetic field of the Earth is filling this room. But if you do something like fire a laser here, right, you get a very intense electromagnetic field at these particular points along the laser beam. Okay? So this is really happening in our universe. So this isn't just a bunch of stuff I'm talking about. So this is what makes physics so cool, right? It's real, right? This really talks about what's going on in our universe. But there's a really nice mathematical description for this laser beam. And this laser beam can actually be described purely in terms of geometry, and actually purely in terms of how a circle is twisting around over our space-time. Okay? Or rather, sets of circles. All right, so what the heck am I talking about? Maybe you know that light along this laser beam has to do with a very intense oscillating electric and magnetic field along this beam. Okay. Well, you may or may not know that along this beam, not only do you have this very strongly concentrated electromagnetic field along these points, but that these electric and magnetic fields describe the change in a single field, which is often called the electromagnetic potential, or it's also called the electromagnetic connection. And it's called the connection for a very interesting reason in terms of geometry. And that is these electric magnetic fields are the derivative of this connection field in space-time. So along that laser beam, you have this intense connection field. But this connection field is describing geometry. Specifically, it's describing the geometry of how circles are attached to space-time at every point in the universe. And specifically, right where that laser beam is, the electromagnetic connection describes the circles as being attached to space-time with this twist in them, corresponding to the oscillation of the field. Okay? So this is a very direct description of electromagnetism purely in terms of geometry. Okay? And these circles, which mathematicians call U1, or actually physicists call them U1. Mathematicians, circles tend to be too simple. But overall space-time, what's going on is you have one of these circles attached at every point in space-time, and how they're twisting over that space-time corresponds to what electromagnetic field you have at that location in space-time. Or if you're talking about particle physics, you're talking about quantized excitations of these circles corresponding to photons at that location in space-time. Now, I want to make it clear that here space-time is this warping fabric that we're in. And these circles that are describing electromagnetism are not in space-time. It's not like you'd go down to some microscopic scale and look and say, hey, look, there's a circle corresponding to electromagnetism. They're not in space-time. That's a different weird theory with different circle-like things. But for this theory, the circles are described as being attached to space-time, sort of perpendicular to it. But they don't have a distance, right? There's no scale associated with them. They don't have a size, right? Scale is associated with movement inside our space-time. And these circles are outside our space-time but attached to it. So we can't travel in that direction, and we don't see these circles, but we see their effect. Their effect is that we see light because of how these circles are twisting over our space-time. Like I said, it's a very nice geometric description. So we don't just have light in the universe, we also have particles interacting with light. What are these other particles geometrically? Well, it turns out these other particles that interact with light also have a nice geometric description. So other charges in the universe that interact with electromagnetism are these other elementary particles, such as electrons, which interact with light, and also up quarks and down quarks, and they're antiparticles, which have opposite electric charges. So these are the electric charges of the elementary particles we know of, and how they interact with electromagnetism is controlled by these charges. So what is this geometrically? And what are these things? Well, like a proton, for example, is made up of 2 up quarks and a down quark. Okay, and their electric charges add, so that's a total charge of +1. And usually has an electron orbiting around it and make a hydrogen atom. That's a total charge of 0. And maybe you know that whenever elementary particles interact, their electric charge is conserved, right? Whenever you have an interaction at a point, you have to have as much charge coming in as going out from the interaction. So why does all this happen, and what's the geometric description of it? Well, it has a very nice geometric description. It turns out that these electric charges, geometrically, are described by how the fibers corresponding to these elementary particles, which exist at every point in space-time, are twisting around the circular fibers of electromagnetism. Okay, so remember, you have a circular fiber at every point in space-time, and then you have these elementary particles that are charged, and those electric charges correspond to the number of times their fibers twist around the circles of electromagnetism. Okay, and that's also why they come in these stepped numbers. That's why they come like this. So a down quark, say, might have 1 twist around the circle of electromagnetism. Electron would have 3, and an up quark would have 2 in the opposite direction. And whenever you have 2 electrically charged elementary particles meeting, what happens is geometrically their twist numbers around the circles of electromagnetism have to add, right? So you get charge concentration as a result. Charge conservation as a result of the geometry. So this is now a nice geometric description for all the elementary particles that interact with electromagnetism. But electromagnetism is not really fundamental. We know that there are these other forces, the weak nuclear force, and this other force called, if you like, the hypercharge force, and that electromagnetism actually is a combination of these other 2 forces. Now, this might be a new idea. So you can see, though, that here the electric charges, -1 for the electron components down here, and +2/3 for the up quarks, and -1/3 for the down quarks. All that's still the same. That just turns out to be a combination of these other forces. So what's going on is these circles of electromagnetism are actually they're inside this other combined Lie group in this electroweak Lie group. And this electroweak Lie group is a combination of 2 other Lie groups. It's a combination of one other set of circles called the hypercharged Lie group, which is U1, and the Lie group of the weak force, which is called SU2. So what's this SU2 thing, and how does it correspond to these charges? So remember I said that electrons and other charged particles, they can twist around the circle of electromagnetism. Well, in a Lie group, you don't just have other fibers twisting around the circle of electromagnetism. You have other circles twisting around that circle. Okay, so a Lie group is something that is constructed by twisting circles around each other, as shown here. Okay, and the number of twists it has corresponds to the charge with respect to that force. Okay, and these Lie groups are, you can only do this in so many ways. So if you take a circle and you twist another set of circles around it, if you don't put a twist in it, you get a torus, right? You just get a donut. So that's how wrapping one circle around another, you get a smooth surface, that's a donut. But if you take one circle and you twist another circle around this and put a twist in it, and then you take a third set of circles and you put a twist in it around the other 2 sets, then you make this 3-dimensional object. That's the Lie group SU2. Okay, and it's a three-dimensional object. You can't really project it nicely down to our space and show what it looks like, but you can talk about its properties and describe its properties. And the easiest way to describe its properties in terms of how the circles twist around each other and plotting that in a diagram. And that's how you get these weight diagrams. All right, and then specifically for the electroweak model, it gets more interesting, which is you take the U1 of the hypercharge force, and you attach that, you have this SU2 Lie group, and you have a circle inside of that. And you combine them into this four-dimensional Lie group. And inside that four-dimensional Lie group are those two circles that don't twist around each other, so you have a torus. All right? And now the other particles, like the electrons and the quarks, now are fibers over that combined Lie group. And they twist around that Lie group, such that they're twisting like this along this torus, so that you map, now you take and you count the number of twists around each one of these circles in this plot, and you plot it, and you get the electron down here. Right? So here it is twisting around the U1 of hypercharge, and here it is twisting along the circle inside SU2. Now SU2, yeah, you have a question already back there.
We snuck in fibers in there and never really
Right. So good. Thank you for backing me up for that. That was an oversight on my part. Very nicely done. So these. When I talk about space-time as a four-dimensional fabric and having a circle attached at each point, these circles are called fibers. And the combined space, the combined geometry of the fabric of space-time and the circles together as one large space, that's called a fiber bundle. Okay. And every elementary particle is associated with a different fiber. And there's one of those fibers at every point in space-time. And its intensity, or it's how those fibers are twisting over space-time, corresponds to the amplitude of having an elementary particle there. Okay.
So they're sort of drawn like electric or magnetic field vector.
Right. It's sort of an arrow. But that's a curious point. So that's kind of strange. What the heck does that mean geometrically? That doesn't make as much sense as a circle twisting around makes for a nice shape. But what's this arrow as a shape? Yeah. This is a graphical way of describing what's called a representation space. But what we'll see is that dissatisfaction you have with arrows is correct. And you can actually describe everything, including the fibers of things like electrons and quarks, not as little arrows, but also as circles that wrap around other circles. So what we'll see, which is very satisfying, is you can actually describe every elementary particle in physics as an aspect of a single Lie group, corresponding to different circles, which is a very satisfying picture. Okay, but you're right to point that out. Okay, so back to this diagram and what it means. This diagram is describing this Lie group geometry. So what happens here is the twists around the circle inside weak SU2 is along the horizontal. So you plot the twist numbers of these forces. So the weak force particles here have twist numbers out here, probably -2 and 2, or -1 and +1. And then there's an arbitrary multiplying factor there. That's why you get fractions. And then the things like parts of these fermions, like the electrons and quarks here, have twists of half that amount in opposite directions around SU2. And then around the hypercharge force, they have this odd pattern of twists. And then there's a special particle that also twists around this SU2 and U1 Lie group. Remember, this is a Lie group corresponding to the electroweak force. So this nice Lie group, SU2 and U1, is this four-dimensional Lie group, but there's this other particle that twists around it, and this is conjectured. This is called the Higgs boson, which is a particle that's referred to quite often, and like I said, it's the main reason the LHC was built, is to look for this particle. And it's sort of these squares and diamonds hiding here behind the neutrinos to mask their importance, because it's actually this Higgs boson that picks out a specific direction inside this combined Lie group inside this combined electroweak Lie group. But you can actually see this inside this diagram. So what happens is this Higgs field, which is another fiber wrapping around the SU2 Lie group, is conjectured to have a constant value in all of spacetime. Okay, so it has a large mass and it fills all of spacetime. And what happens is every other particle interacts with it and picks up a mass. And via this interaction, that breaks the symmetry of this electroweak Lie group. So it has this odd number of twists around the electroweak Lie group. But when this gets a mass, that picks out this direction inside the Lie group and inside this diagram. It turns out to be an angle of about 38 degrees in this diagram. And now that sets the electric charge of all these particles and how they interact with the U1 electromagnetic field inside this Lie group. So now the U1 of electromagnetism corresponds to this direction in this diagram, which is perpendicular to this line formed by the Higgs boson. Okay, so this is how the Higgs boson breaks the symmetry of the electroweak interaction, such that you get electrical charges of -1 down here for the electrons, and plus 2/3 up here for the up quarks, and -1/3 down here for the down quarks. And this comes from how the Higgs boson here breaks this electroweak pattern. It's a nice graphical picture of symmetry breaking. But remember, what's going on is that this diagram is describing this geometry going on with these Lie groups of circles twisting around each other, and picks out this direction in this Lie group. It's a nice geometric picture, and this diagram helps portray that. Okay, so rotating this back, we have this nice picture of the electroweak model and the electric charges of particles as a result of their weak and hypercharge, their weak charges and their hypercharges, which correspond to the twists of fibers around these Lie groups. But now I want to talk about the strong force, okay, the strong nuclear force, and how that works. Well, for the strong nuclear force, you have an 8-dimensional Lie group, consists of 8 sets of circles all twisting around each other in a very nice pattern. And if you plot out their twists, right, you can take these 8 sets of circles twisting around each other that are the SU3 Lie group. And remember, there's one of these at each point in space-time now. And you can take 2 of them, and you can find 2 of these generators that don't twist around each other. So you have a torus inside this SU3 Lie group called a maximal torus, if you're a mathematician. And the other sets of circles twist around these 2. And when you plot what their twists are around this maximal torus inside SU3, it makes this nice hexagonal pattern. So these are all the gluons corresponding to the particles of the strong force. And their charges, in terms of the twist numbers around the 2 circles in the torus, which are drawn along these 2 axes, G3 and G8, right, makes this nice pattern. Okay, so this pattern describes the structure of this nice twisted bit of geometry. Okay, these patterns, which are called weight diagrams, really portray the geometry of these Lie groups. And the fibers now that interact with the strong force and twist around this SU3 Lie group are the fibers of the quarks, right? So each quark, up or down quark, has what's called a color assigned to it. And that color corresponds to its charge. It corresponds to its twists around the SU3 Lie group. So each quark, say each up quark, has 3 different colors. Here, green, red, and blue, corresponding to where it sits according to its charge, according to its twists around SU3. And the fact that it makes this triangular pattern, the mathematical term is this is a representation of SU3. It's referred to a nice sort of concise pattern. But the fact that it is this triangle is why Gell-Mann came up with the name to refer to them as colors, right? Because it's like having 3 primary colors that are mixing. And whenever you have something like a proton that's made of 3 quarks, the strong force is so strong that it has to be color neutral. You have to have 1 quark of every color, adding up to something that's color neutral. Otherwise, the force would be too strong and immediately pop other colored quarks into existence to cancel it out. So anyway, this is a nice, also these other particles here are the anti-quarks. They have the opposite twists around SU3. Now, remember, for the electric charge, whenever particles interact, their twist numbers have to add. You have to have charge conservation for every interaction. And the strong force is no different. When you have quarks interacting with gluons, what you actually have geometrically is their twist numbers adding. So when you have a quark flying along a nucleus and a gluon comes and hits it and interacts with it, it turns it into a different quark. And all the charges have to balance. So say this gluon over here interacts with this green quark. What happens is you get this red quark as a result. And this is a strong interaction. Okay? And all these charges, as shown here, have to balance. So these weight diagrams, they aren't just pretty, and they don't just describe the Lie groups. They also describe what interactions are possible. Okay? It describes when interactions happen. So they're very useful. And so now we have, having introduced and described the strong force, we can combine the strong force with the description of the electroweak force and get this nice pattern that describes all the interactions of, in the standard model of particle physics, which is to say you have the electroweak model, which, remember, has a two-dimensional torus associated with it, one of hypercharge and one in the SU2 weak force. And then you also have this two-dimensional maximal torus of the strong force and all the twists around that. And you can, when you combine them, when you take the strong Lie group and you twist it around the electroweak Lie group, you get this combined Lie group, which, since the U1 is one-dimensional and the weak force is this three-dimensional SU2 Lie group, and the strong force is this eight-dimensional Lie group. Here we're talking about a 12-dimensional twisted geometric object with a four-dimensional torus in it, and we're plotting the twists. We're plotting all the twists around this four-dimensional torus with a set of twists around each one of these four directions. And this is the diagram we get. It's a diagram that exists in 4 dimensions, but now we project down to 2 dimensions so you can see it. Did everybody follow that? Yeah, one question.
What's W and Y?
Yes. So W corresponds to this circle in. So we have this weak SU2 weak Lie group corresponding to that's SU2. So the Lie group corresponding to the weak force is SU2. And inside that Lie group is a circle. And we count the twists of other circles and other fibers around that circle inside SU2. And we plot that twist number along W. That's a particle's weak charge. The number of times a particle twists around that circle of SU2 is its weak charge, W. Yep. And Y is the same thing for the hypercharge. So we have this circle called U1, and a particle's hypercharge corresponds to its twists around that U1, and we plot that along Y. So for elementary particles, we're not sure why yet. I haven't said why yet, but they have twists of plus or minus a half around this weak SU2. Those are just their charges. Nature happens to be that way. Why does it have that pattern? That's a deeper question. But this is the pattern we see. But the deeper question is, why does it have this pattern? Okay. All right. So now you understand. Now you understand the game of what's going on, I hope. Okay. Oh yeah, crystal clear. All right, I'll run through it one more time. So we have. Okay, G's. Okay, so the G. So there are two little G's here, the G3 and the G8, and they're small here, right? Because of the way I've done the projection. Right. So it's like you can take this diagram in 4 dimensions and just flatten it down to 2, and you can do that such that you see whatever pattern you want as a result. So it's kind of arbitrary how you make this projection because you're projecting a 4-dimensional thing down to 2 dimensions. But you see all 4 axes. And the G3 and the G8 axes, remember, are now the 2 different circles in the maximal torus of SU3. So what you're seeing here is the twist numbers around this maximal torus in SU3, and plotting these, one along the G3 and one along the G8, each corresponds to a set of circles in SU3. And these are the strong charges of particles. So whenever you have an interaction in the standard model, right, any particle interaction at all that we know of has to correspond to adding these charges together in this 4-dimensional diagram in such a way that they all balance. And since you're doing a projection, that means that they have to balance if you do it in 2 dimensions also, visually. So these weight diagrams are really cool for playing around with particle interactions to see what can happen. And it also uniquely describes the geometry of these Lie groups. Okay, so they're not only are they useful and visually appealing, but they're very powerful for describing these particle interactions. And now you have a hint of the geometry that's behind them, right? It's not these patterns themselves that are over every point in space-time, remember. It's these twisting Lie groups that are over points in space-time. And these patterns describe the geometry of these Lie groups and the other fibers twisting around them. Okay. Yes. Yes.
Quick aside, have you ever managed to devise a model of this physically?
Physically? You're living in it.
No, I mean,
Oh, you mean like a 3-dimensional model?
well, yeah, or
or higher. Yes, yeah, you can play with there. It is fun to play with models of these things. I tend to do all my work on the computer. All my stuff is entirely digitized, but you can play with this, and I can imagine I've seen some toys that take advantage of some of these symmetries and can portray them. All right, so this deeper question of why this pattern. Okay, remember all this is entirely. So far, I haven't even talked about anything weird yet. Right? This is just the conservative geometric description of the standard model. Okay, there's nothing even weird here. So now I'm going to talk about something more speculative, which is why has nature chosen this pattern? Okay? That question of why always gets you after you ask it enough times and you get down to the bottom of things, right? So this will go away in a second. With the standard model, remember the SU2 of the weak force, U1 of hypercharge, and SU3 of the strong force. Physicists only came to this probably around 1972, 3, 4, around then. And almost immediately they noticed that this collection of Lie groups, very conveniently because of its structure and how the fermions, electrons and quarks, wrap around and have charges around this Lie group, allows something really remarkable. And that is this particular Lie group fits in this slightly larger one, SU5. Okay? So that these Lie groups could be parts of a larger Lie group. And this would sort of describe why it has the structure it does. They postulated that you could have this larger Lie group, and via a mechanism, like the Higgs mechanism, its symmetry would break down to the symmetry we see of the standard model, and then further break via electroweak symmetry breaking and that Higgs down to electromagnetism and the strong force that we see. So they had this SU5 theory, that all the standard model Lie groups could fit in this larger Lie group of SU5, which I think is a 5 squared n squared minus 1. It's a 24-dimensional Lie group, 24 sets of circles twisting around each other. And then there was this other model developed around the same time, around 1974, I think, where this SU5 model, which includes the Lie groups of the standard model, fits in yet a larger Lie group called spin 10. And this spin 10 Lie group corresponds to rotations in an abstract 10-dimensional space. But this Lie group itself, you can remember, just think of as a bunch of circles twisting around each other. And it has a name. Mathematicians called it something different, but physicists call it spin 10. And it corresponds to the rotations in 10 dimensions. And I'll talk about this sort of thing also and how it relates to gravity. Okay, so there are these other Lie groups that you can fit the standard model in. And it's not just the structure of these interactions that allow this to happen, but the strengths of these forces, as you go down to smaller and smaller scale, appear to converge. So if the strengths of electromagnetism, the weak force, and the strong force, which are all very different at our scales, okay, as you go down to smaller and smaller distances, they start to converge and look like aspects of the same force with the same strength. Okay, so that's another reason to believe this unification actually might happen. So this math sort of describes what's going on, but it's actually very nice to look at how these unifications work in terms of the structure and the weight diagrams for these models, and how the standard model embeds in these other things. Yeah.
What are the axes for this?
This is roughly energy and strength of force, or actually 1 over strength of force. Sorry for not putting units on it. I just wanted to give a rough idea of the convergence without scaring too many people. All right. So, back to our friend, the standard model. Why this pattern? And why this collection of things? We have this motley crew of Lie groups here acting with a bunch of fibers wrapping around it in this odd collection of charges. Why this pattern? Okay. Well, it turns out, as I said, that this Lie group fits inside SU5. And when you do this embedding in SU5, you'll see that SU5 has a bunch of other particles corresponding to other circles inside SU5. Because remember, the standard model had 12, and SU5 has 24. So 12 more are going to pop up, corresponding to 12 new particles. So that would correspond to a new force. And these particles in SU5 are called X bosons. So what's that look like? It looks like this. So that's SU5. And now things have simplified dramatically. Now you only have one Lie group for the forces and 2 sets of fibers wrapping around them corresponding to the electrons and quarks. And some new particles have appeared. So now we have these other particles, like these here and these guys here. There are 12 of them. These are called the X bosons in the SU5 model. So when they figured out this embedding, they said, well, if this grand unified theory, combining all the standard model forces into SU5 is correct, then we should see these X bosons and see the effects of having these X bosons around. But we don't see them. Okay? And they said, well, we don't see the particle accelerators, but there's something even worse, which is if these X bosons are actually around, they'd allow behavior to happen that we don't see. And that is they'd allow protons to decay. And we're all made out of protons, so we'd really notice really quickly if they were decaying. All right, so what the heck am I talking about? Well, you actually see exactly what goes on using this diagram and by balancing out these interactions. So remember, a proton is made of 2 up quarks and a down quark, each of a different color, because it has to be overall color neutral. So proton, up quark, down quark, all different colors. Total charge of +1, and interact with a strong force holding together happily. But what happens when you have this X boson? Well, if this X boson, which doesn't normally exist in the standard model, with that X boson, this down quark here can decay. It can change into this X boson plus this positron. All right, so if you add these, if you do vector addition and add these two, you get this quark over here. So this is how particle decay happens. Okay, so you have this proton sitting here. It can just change into still those 2 up quarks, and then now this X boson and this positron. Okay, this positron being an anti-electron, which just flies off, all right, carrying the charge of the proton, +1. But then what happens is this X boson can interact with the other up quark and change into this anti-up quark. So now what's happened is your proton has changed via this X boson into a positron and this quark and anti-quark pair, which is called a meson. Okay, it's called a pi-naught meson, which then flies off in another direction. So if this SU5 model is correct, you should see this proton decay. And theorists thought, well, okay, maybe protons just decay every once in a while, so we don't notice it, but it's actually happening. And experimentalists, being ever skeptical, they actually said, well, we're just going to watch a whole bunch of protons and see if this decay happens. And if it doesn't happen, you theorists are wrong. So that's what they did. They got this huge cavern and filled it with 50,000 gallons of water and cleaning fluid and put this array of photomultiplier tubes around it, such that if a proton decayed inside this huge vat of mostly water, it would release this high-energy positron, and you'd see radiation as a result that they detect and say, there's proton decay, so there must be some X bosons allowing that to happen. So they did this. They sat and watched this huge cavern of water for a very long time and didn't see any proton decay. And the theorists were not able to successfully twiddle their model to be able to get above the limit that the experimentalists were excluding. So this SU5 model was now ruled out because proton decay was not seen. Okay, but on to the other grand unified theories. Yes?
Is there a predicted half-life for this decay?
Yes. It's on the order of the age of the universe. but it's well, the thing is you can get a lot of protons into a huge vat of water, such that you balance out that other huge number, and you actually should see a few. It's just you watch enough of them, and you're going to see it happen. All right. So, but theorists try to get that number higher so that you wouldn't see it, and that's the game. And you can't do it in this SU5 nicely, but you can do it in spin 10. So this SU5 model fits inside spin 10. So now this embedding happens inside spin 10. And now you have a few more particles here that actually overlap some of the fermions, but are yet more X bosons in the spin 10 model. And here theorists are able to play with the numbers such that proton decay happens at a slow enough rate that you wouldn't see it, and it hasn't been rolled out yet. But it could be. So you need to watch more water for a longer amount of time. But it's sort of a joke that people who believe in grand unified theory are people who sit around waiting for a proton decay, right? And haven't seen it. So it's kind of disappointing. So there's probably something else at play. But still, it's fascinating that these unification models work structurally and also for the strengths of the particles converging. So they're telling us something, but we're not quite exactly sure what. But there's some kind of unification probably going on. Now, this spin 10 model is even, in a way, prettier than the SU5 model for a couple of specific reasons. When you project down here, you'll see this array of charges, which sort of has a more complete pattern to it. And you can rotate it around now in 5-dimensional charge space. There's now another circle orthogonal to the other 4 of the standard model now that you can have in SU5 and spin, or that you can have in spin 10, not SU5. But in spin 10, you can now have a 5th circle, making a 5-dimensional maximal torus, corresponding to a 5th kind of, corresponding to a new kind of force. But anyway, what's really special here is the pattern of electrons and quarks and neutrinos in this spin 10 grand unified theory. It's a really pretty pattern. Instead of in different representations, all these fermions of one generation just sit in one representation space. It makes a nice pattern. So this doesn't look really pretty like this because the standard model is a little ugly and fits in it. But if you rotate this spin 10 grand unified theory in this charge space, you can see that it's a really pretty pattern in this 5-dimensional space. And you can project it out, and it looks sort of like that. So you can see here, it's a really nice pattern, and it's a nice pattern for a fantastic reason. It's a nice pattern because this spin 10 grand unified theory, which consists of all these circular bosons which correspond to the different circles inside spin 10 twisting around each other. And then separately, we were talking about the fibers of the electrons and quarks twisting around this spin 10 Lie group. But here what we see is that those fibers of the fermions actually themselves, combined with spin 10, are part of a larger Lie group. Okay? And this is one of what are called the exceptional Lie groups, E6. And this is really an amazingly cool thing because it means we have this other unification going on. Not only now are all the forces, except for gravity so far, sorry, this is going to be a longer talk, because you know that's coming up. You have not only are all the forces, the electroweak and strong forces combined in one Lie group, but all the fermions, all the matter particles also are part of the same Lie group, part of this E6 Lie group. And it makes this very nice pattern. So you have, it's something better than a grand unified theory. You sort of have a super grand unified theory because you've included the fermions too. And people have known this for a fairly long time, but haven't known what to do with it. So E6, what's E6 and what are, I talked about classifying these Lie groups. What are they? Well, mathematicians figured out around 1900 how to classify and describe all these different Lie groups. There are 4 infinite sets of Lie groups that basically correspond to larger and larger rotations. Say rotations in higher and higher spaces, you have circles twisting around each other to describe these rotations, and you can go arbitrarily large. And this is just, as terms of the Lie groups, there are only so many ways you can twist circles around each other consistently to make these shapes. Okay, and mathematicians figured them all out. But as well as the 4 classical infinite sets of Lie groups, there are 5 exceptional cases. Okay, there are 5 special ways of twisting circles around each other. And these are called the 5 exceptional groups. And E6, which we just saw, is composed of 78 circles all twisting around one another. And they go all the way up to the largest simple exceptional Lie group of E8, which is 248 sets of circles all twisting around each other in a very exquisite pattern. All right, so this E6 theory would be very, very satisfying as a theory if not for what Jeff described as the most important force in the universe, which is gravity, which so far particle physicists, despite all the fun they've had, have almost completely ignored. But I'm not going to ignore it. I don't particularly care that much about what other particle physicists are doing. I live out in a rock in the middle of the Pacific Ocean, right? I can do what I want. And I wanted to figure out how gravity comes in and works along with these forces of particle physics. And it turns out to be related to spin. Okay? This is a frame from a cartoon that was published, I think, 3 days ago. And it describes my life for the last 15 years, which I thought was great. The cartoon actually is called Abstruse Goose, if you want to look up. I'm convinced it's absolutely the geekiest cartoon in existence. But it turns out that understanding what spin is and how it relates both to particle physics and to gravity is the key to understanding how everything fits together in one unified picture. And the rest of this talk, I hope to give you a very satisfying answer to this cartoon and tell you exactly what spin is. And not only tell you exactly what spin is, but tell you exactly why spin is, which is an even more satisfying answer to have, if it's right. Not sure it's right, but it might be. Okay. So now let's talk about spin. There's a Lie group corresponding to the rotations of objects in three-dimensional space. This Lie group is called spin 3, spinning things in 3 dimensions. Fairly straightforward. We're sort of familiar with this. You're rotating something around, and you're playing with points on the spin 3 Lie group, which is this continuous surface. And as a three-dimensional manifold, it's this abstract thing that corresponds to how something is rotated, right? But as a three-dimensional manifold, it's sets of circles twisting around one another in a specific way. And specifically, you can break this up into 3 sets of circles that you can then describe other rotations with respect to. So, for example, physically, if I take this this arcane object, I'm not sure what it is, but it seems useful as a visual aid. You take this and you can rotate it along 3 different independent planes. Okay, you can rotate it along this plane, right? Or you can rotate it in this plane, or you can rotate it in this plane. Now, as a Lie group, these different rotations, twist around one another in the Lie group. So what that means physically is that these rotations interact with one another. Now, in terms of elementary particles, what you'd say is there's a different elementary particle corresponding to each one of these rotational planes, and they interact according to the geometry of this Lie group. Now, what is this geometry? Well, if I take this, how does this interaction work? Well, physically, if I take this and I rotate it 180 degrees along one plane, so look, it's facing up and towards you this way. If I rotate it 180 degrees in this plane, and then rotate it 180 degrees in this plane, okay, that is equivalent to a 180 degree rotation in this plane. Right? You guys are intuitively familiar with this. So this is how interactions happen in particle physics, is due to these interacting symmetries of these Lie groups. Okay, just like this interaction happens for this rotation. Okay, so it's a very nice geometric thing. Now, fortunately for us, things are happening in the universe. It's not just this static symmetry of spin 3 that we have in space. Okay, this is the symmetry of space, but we don't just live in space. We're actually living in space-time. We're all traveling forward in time together through space-time. And the symmetry group of gravity, of the force of gravity, is not just spin 3, it's spin 1-3. It's the symmetry rotations in 1 time and 3 space dimensions. And we actually see this. This is described by this wacky theory of special relativity. Okay, so not only can you rotate now in 3 planes, but now you can also rotate from each one of these perpendicular 3 directions into time. Which is to say, this book can be moving in any of 3 directions with some speed, with some velocity. Okay, and as it moves in some direction, right, it rotates in space-time. So you'll actually see. So if I rotate this in space, right, or maybe look at the projection here, you'll see it get shorter as I rotate it. Okay, well, this actually happens if this thing has some velocity. So if I give this thing a velocity this way, right, you see what's called a Lorentz contraction. Right? You'll see the book get shorter along its direction of motion. Okay? And also, if this thing has a clock on it, this clock will tick. You'll see it tick more slowly. Okay? That's called time dilation. And we actually know this happens. So if you have some particle that's whizzing along with some high velocity near the speed of light, then you know that particle decays on average at a certain amount of time, you'll see it live longer because of the time dilation. And that's because it's rotated in space-time. Now, this sounds like an odd thing, but we're used to seeing these sorts of rotations in 3-dimensional space, but this is a rotation in space-time. So you actually see it get shorter along one direction like this, and you see the clock tick longer. You don't see it get longer in this direction as I do from my perspective. Okay? So these space-time rotations are really neat. And like I said, the Lie group of gravity is spin 1-3. Okay? It's this group of rotations, 3 in space and 3 into space-time. What's this mean for describing the gravitational field? Well, the gravitational field, a good way to think about it, is you have this connection corresponding to gravity. So you have this spin 1-3 connection, just like the electromagnetic connection describes how these circles are twisting around over space-time. The spin 1-3 connection describes how the gravitational frame is twisting over space-time. Now, what the heck is a gravitational frame? It's a ruler over here. Gravitational frame is, in order to describe the fabric of space-time itself, you need something to measure distance on that fabric. And that's what the gravitational frame is. It's also, you can call it the metric. But if you take a ruler and imagine it attached to every point of space-time, and then you take two more, so you have three orthogonal directions to span your three-dimensional space and space-time. And then you also add a clock. The cell phone has a clock in it at that point in space-time. This is equivalent to the gravitational frame. Okay? It gives you direction and distance in three different directions, and a fourth distance in time via how fast the clock is ticking. And the gravitational spin connection tells you how this frame, the gravitational frame, changes from every point in space-time. So here's a picture of now the fabric of space-time with rulers and clocks. Here's a clock, and here's a ruler. And the spin connection tells you how this gravitational frame changes over space-time. So this is a very nice description of gravity. So what this tells you, the way thinking about gravity this way tells you that what's going on as you're sitting here in this room is we're all moving forward in time together, right? And the Earth has this gravitational spin connection field around it. And that spin connection field is trying to give you a velocity towards the center of the Earth. It's trying to rotate. As we move through time, it's trying to rotate us such that we're space-time rotated and pick up a velocity towards the center of the Earth. Okay, and this is what the gravitational field is. Yeah. So remember, the spin connection tells you how the gravitational frame is twisting as it anywhere on the space-time fabric. Okay, and each of us we carry our own space-time frames with us, right? So we know how tall we are, and we know how fast our clock is ticking, and we can feel those things, and we perceive them based on where we are. And the gravitational field comes and tries to rotate us as we move around in space-time. So as we're moving forward, we're all moving forward in time. And as we do that, because the spin connection is there over space-time, the gravitational spin connection is trying to rotate our frames and give us a space-time rotation in the plane of time and the z-axis being vertical. So that's the rotational plane that the spin connection of the Earth is acting in. So it's trying to give us, by giving us that space-time rotation in t and the z-axis along that plane, that's trying to give us a velocity towards the center of the Earth. And the only reason we're not accelerating towards the center of mass of the Earth is because we're pushing against it with our feet or other parts. So it's a really nice way of describing gravity. And it also is consistent with Einstein's description of gravity as this warping fabric with this gravitational frame over it. He was always talking about rulers and clocks and space-time and describing gravity that way, which is also consistent with describing it with a metric, which is a distance in time and space on the manifold. All right. So this is what spin. How the spin group of gravity acts on things. How does this relate to what's this have to do with quantum mechanical spin of particles? Well, this gravitational frame. I had this book, but I'll go back to using the cell phone. So this, if you consider this cell phone, right, and how the spin group acts on this cell phone. If I take this cell phone and I rotate it 360 degrees, right, it returns the same state it started in. So in terms of as a fiber, right, if this corresponds to a particle that's a fiber that's wrapping around the spin 3 Lie group, you'd say it has a spin charge of 1, right, because it wraps once around the spin 3 Lie group. You act on it with the spin 3 Lie group around 360 degrees, and it returns to where it started. It's a fiber that closes after going once around this spin 3 Lie group. Okay. An electron does not work this way. Okay? An electron, or a quark, has a spin charge of 1/2. So if this were an electron, you rotate it 360 degrees, it has not returned to its starting place. You have to rotate it 720 degrees in order to get back where it started. And this is because an electron, unlike the ruler, unlike the gravitational frame, has a spin charge of 1/2, not a spin charge of 1. So this is what spin is. This is my answer to that cartoon. Spin is rotational charge. It's the number of times these charged particles as fibers are wrapping around this spin Lie group. There's actually a marvelous analogy for showing how something can need 720 degrees of rotation to return to its original state. So if you keep your eyes on the cell phone, I'm going to keep it flat and rotate it 360 degrees, and you'll see it does not return to its original state if I consider the cell phone and my arm as one system. So if I rotate this thing as flat as I can, 360 degrees, you'll see there's a twist in my arm. But if I keep going another 360 degrees, holding it flat, it returns to its original state. So that's a nice visual analogy for seeing how something can take 720 degrees of rotation to return to its original state. And electrons and quarks are like this system. They have to go twice around the spin 3 Lie group in order to get back to the original state. They have a spin charge of 1/2. All right, so now we know we know what the electroweak and strong charges are, and now we know what the spin charges are. We can plot them on these weight diagrams for the spin 1,3 Lie group. And the gravitational frame field, now as a fiber, has to have spins of plus or minus 1/2 with respect to this two-dimensional. It's actually a hyperbolic torus inside spin 1,3. And these other fibers twist around this with these twist numbers of plus or minus 1 for the frame and plus or minus 1/2 now for the electrons and quarks. And these other things are the gravitons themselves twisting around this Lie group. Remember, it's a 6-dimensional Lie group, 2-dimensional maximal torus. These are all the twist numbers. You plot it, there it is. Well, this is great because now we can take these charges and combine them with all the charges we know of with respect to the standard model and see what we get. Okay? And project it down. Because now, with the standard model, we've got this 2-dimensional torus of the electroweak model, a 2-dimensional torus of SU3, and now we have this 2-dimensional torus corresponding to the spin 1,3, all wrapping around each other. So we have 6 charge axes, including spin. We can all project down, and we see the whole zoo of elementary particles and their states in one diagram. It's kind of a mess. Okay? But now we can play the same game again. Because remember, this is just the standard model and gravity together. What about these unified models? What do they look like when you combine them with spin? Well, the spin 10 unified model makes things look like, like I said, the whole zoo. So then the spin 10 model makes things look like that. It helps complete this diagram. Okay? Things start looking like they come from a more coherent picture. And they start to have, so remember now we've got all the charges of the standard model, okay, strong charges, electroweak charges, and the charges of gravity, the spins that these particles have, all projected down from this high-dimensional diagram corresponding to their twists around this high-dimensional Lie group, down into this two-dimensional plane to make this pattern. So not only does it make this cool pattern, but the unification itself, described down here, is very efficient. Because remember, gravity, I said, was described by the spin 1,3 Lie group. And this grand unified theory that we're holding on to, waiting for protons to decay, remember, was a spin 10 Lie group. So it's very natural to combine spin 1,3 and spin 10 in spin 11,3. Right? It's the first thing you try, and it works. And the extra particles you get after you do, so usually when you do this unification, right? Remember when we do this unification for grand unified theories, we've got these X bosons. But when we do this unification for spin 10 and gravity, the particles we get are particles we want. Because what the particles are that you get from this unification are the gravitational frame and the Higgs field, which is fantastic. Okay, those are fields we want, because those were just other fibers that we didn't have an explanation for. But now we can see they're part of this spin 11,3 Lie group, and exactly the way we want them to be. And we can plot them out here. So here's the frame and the Higgs out here. Very, very nice unification. And the fermions are in this nice pattern now of 64 states for one generation of fermions. And now this pattern is kind of nice. And it's kind of nice in the same way that the spin 10 grand unified theories was nice, because this pattern of spin 11,3 and the fermions, all as one weight system, this structure of particles interactions actually fits perfectly inside the E8 Lie group, like this. That completes it to E8. So now that we can see that the standard model and all these force particles are parts of this exquisite E8 Lie group structure, and exactly how they're part of that structure. It's really a wonderful, wonderful thing to see, and there's no reason it had to happen this way. But it does. Now, the mysterious thing is there are a bunch, when you do this unification inside E8, there are a bunch of other particles left over. There are different ways of interpreting this. If you interpret them directly, there are things that you don't necessarily want.
When you say leftover, what do you mean?
I mean, it predicts particles that we haven't seen, which is usually bad.
Are they in there?
Yeah, so they're those. There are a lot of them. All right. This is another projection from this E8 Lie group. It's a very pretty thing. So inside this E8 Lie group, remember you've got 248 sets of circles twisting around each other. You have an 8-dimensional maximal torus. You plot out the twists of all the circles around this 8-dimensional maximal torus to make this great diagram in 8-dimensional space. You take this diagram and you flatten it down to the page any way you want. And here's one way, one projection that gives you a lot of concentric circles. It's very pretty. Also looks good on a T-shirt. Okay, but it predicts, if you do a direct decomposition, it predicts this whole menu of other particles that we haven't necessarily seen. I mean, it has the standard model particles in it, but it also has a lot of other stuff. So people who criticize this theory, including myself, say this other stuff is bad and that we don't see it. And although you can arbitrarily assign large masses to it, that's just like playing this game of proton decay where you just make that number bigger of something this theory is predicting that you don't see, such that you don't conflict with experiment. But that's an evil game. You don't really want to be playing that game. It means something's probably not right about your model. Now, I'm trying other ways to do symmetry transformations in this Lie group so that instead of these extra particles it's predicting being bad, that you will see these particles identified instead as the second and third generations of the fermions. And there's a symmetry in E8 that lets you make that relationship and play with it, and that's what I'm working on now. But before I can get that to work, and I don't have it working perfectly yet, before I can get that to work, E8 provides this finite menu of particles that might be seen, which itself is a prediction, because if the LHC sees some particles and it's on this menu, right, then I'm very happy, right? But if the particles come and they're not one of this set, it means this E8 theory is wrong about nature. And the E8 might see some other superparticles or some other particles that don't have these charges and fit in this pattern, in which case this theory is gone. Yes?
So what does it mean second or third generation?
So remember, when you're talking about one full generation of particles is the up quark, down quark, electron, and neutrino. That's one generation of fermions. And each one has 8 different states. So that's 64 total. As far as we know, all the matter we see is made up of these first generation particles. But in these particle accelerators, we see that there are other copies of these particles with exactly the same charges, but higher masses, so that we don't see them until we go to higher energies in particle accelerators. But as far as we know, there are 3 complete sets. And the last one, the tau, was just seen fairly recently. But everybody knew it had to exist to complete the pattern for a long time now. But it's a mystery as to why there are these 3 sets. So, but because they have the same charges, they don't make a new pattern. But there's this other symmetry of E8 that might allow you to relate 3 sets of 64 things inside E8 in such a way that you can identify them with the generations. So that's what I'm working on now, is you have this triality symmetry inside E8 that helps to relate the 64 first generation fermions to 2 other blocks of 64 things that currently in E8 are things you don't want anyway, but that might be, if I can get the theory to work out right, might be the second and third generation fermions, which you do definitely want. And even better would be if you come up with masses for these things that agree with their measured masses to come out of particle accelerators. So this is the theoretical game afoot, and the current state of things. Yeah.
I remember, like, when Delmon came up with SU3 in the park, that was in the 60s.
Yeah.
And I think it was in the 70s where they figured out some of the dynamics, and they
Yep.
couldn't predict the masses of individual particles, but the differences. So they
Mhm.
said, well, here we discovered this particle, there should be another one, and it should be so much, more mass, more energy.
Yes.
Can you do that?
I see hints that if things work out, I should be able to do that.
Yeah.
But should's a wonderful word. What happens is in the standard model, all these particles like electrons and quarks. You have the up and down quarks, and then you also have the second and third generation quarks, the charmed and strange and bottom and top quarks. And they all have different masses. But their masses don't correspond exactly to their charge states. So their mass states are different than their charge states. So you have this rotation matrix called the CKM matrix that is a rotation applied to the quark states that says how these quarks all mix and get the different masses they do as the eigenstates of these matrices. And nobody knows why these specific matrices are what they are. And what I hope is that these matrices come out and these mass differences between the particles come out as specific rotational angles having to do with this triality symmetry inside E8. This is what I would like to see happening. And I'm seeing some hints that something like this may happen, but I don't have the details worked out yet. Yeah.
A couple questions from the web. They're asking, what exactly do you mean by fibers?
Fibers
again.
Can I take that towards? I will open everything up to questions at the end. Can I wait until then for that? Okay.
No problem.
I love people looking in from outside, from the windows outside. That's classic. And that's some out of the box thinking. It's fantastic. No, it's a really good idea. I didn't even think to open up. Okay. It's Maui, why not be outside? Okay, there's so this theory isn't all pretty pictures. I mean, I didn't even know. I mean, for me it was fantastic because I was working on this for a decade and working mathematically with the structure of these theories, and then it was only a few years ago that I saw this embedding inside E8 and then saw all of these weight diagram ways of portraying these theories. This is only a very recent thing that I saw and was just blown away that you could graphically portray these different theories and embeddings. It's really fantastic. So in that regard, I've spent this whole talk now sort of building up to this unification inside E8 of showing how the electroweak model combined with the gravitational spin and the strong SU3 forces as well as these forces of gravity all embed inside the E8 Lie group. I've built up to this. But now I wanted to go the other direction and say, if this theory is really right about how the universe works, what this means. What this would mean is that you only have one fiber bundle and that each fiber at every point of our four-dimensional fabric of space-time is this E8 Lie group. And the Higgs mechanism is what picks out this direction in this E8 Lie group. So you have this constant set of directions inside E8 picked out via symmetry breaking, which then breaks the E8 Lie group down to what we see as our collection of electromagnetic, weak, strong, and gravitational forces. And when that symmetry breaking happens, in terms of cosmology, since this Higgs field is connected to the gravitational frame field, this corresponds to the frame coming into existence. So the moment of symmetry breaking is itself the moment of the Big Bang. It's when our universe is created. So it's a very nice picture of cosmology that's now partnered with the symmetry breaking of particle physics. It means since you have this unified theory of particle physics and gravity, when you have the symmetry breaking process of this E8 unified structure, you're talking about not only the symmetry breaking of the standard model with the Higgs field, but you're talking about the Big Bang itself, where the gravitational frame and the flow of time itself comes into existence inside the E8 Lie group via the symmetry breaking. It's really a fantastic thing. So what's this look like? Well, what I want to do is take this E8 Lie group, which has all the structure I've described for this whole talk in it as parts of it, and rotate it and show you the various parts that are inside of it. So if I take this E8 Lie group, which is a pattern that exists in 8 dimensions, right, that describes all the intricate twists of this E8 Lie group, and I'm projecting it down to 2, and I'm going to rotate it such that the projection changes to show you the different parts of it. So rotating this thing in 8 dimensions, you can project down and see that it has the electroweak model as part of it. That's part of its structure. And here's the Higgs field here that breaks the pattern and gives you electric charges. So here's the -1 for the electrons in the W field. Here's your +2/3 for your up quarks and your -1/3 for your down quarks. Okay? You want to see it again? I'll run it again at the end, because I'm going to keep going. So now I can rotate from this to spin. Remember, this is still rotating E8.
And are you rotating around a certain axis or about multiple axes?
It's better than that. Yeah. All right. So there's because remember this is a diagram, an 8-dimensional space. So I'm rotating in order to make the projection, I'm collapsing this 8-dimensional diagram onto a 2-dimensional plane. So what I'm actually doing is to determine the projection, I'm rotating this plane in this 8-dimensional space. Okay? So, and this plane is determined by a horizontal and a vertical axis that span the plane that corresponds to the screen here. And so you're rotating that plane. Well, how do you figure out a rotation in 8-dimensional space to show this pattern? So I know where the patterns are, but I have to figure out a path in rotation space that takes this from one plane to another. So, but you have to do it in such a way that the h and the v stay perpendicular in this 8-dimensional space. So it's actually a really cool constrained optimization problem. So I almost melted my laptop making these projections because I had Mathematica running. So I've got this constrained minimization algorithm running to run all the steps to figure out this rotation in 8-dimensional space in order to make this animation. So it's pretty neat. So okay. So anyway, here's the this is spin, where all the fermions having spin plus or minus 1/2, and the gravitational frame here having plus or minus 1, and the gravitons out here, all part of the structure of E8. Also, then I'll rotate out the strong force. Okay, so now we have all the SU3 gluons and all the quarks with all the different colors and their anti-quarks, all as part of the structure of E8. So like I said, I was really amazed to find this visual representation, and even more amazed to find out that not only did it all work, but that it was really pretty. Yeah. So it's really a beautiful structure. And usually when you talk about mathematical beauty, you're talking about an abstract way of mathematical structure going down and interacting in different ways, and you're talking about sort of an abstract kind of beauty. But by these visual weight diagrams for these Lie groups really sort of bring out the beauty of the mathematics in a very immediate, visually striking way. Yeah. And I suppose if you want to play with it yourself, I've worked with a friend of mine to develop this web page. It's a Flash application that will allow you to make these rotations yourself online. It's called the Elementary Particle Explorer. Like I said, also looks good on a T-shirt. But if you Google for Elementary Particle Explorer, so if you Google for Elementary Particle Explorer, you'll get to this thing. At which point you can choose how you want to rotate your h and your v axes inside 8 dimensions so that you can see all these particle models. And so you just go here and rotate these things.
When you put that in 3 dimensions, it would definitely melt the computer, right?
Yeah. Although a friend of mine also burned it into glass with a laser, so made a little 3-dimensional model projection of E8. It's pretty cool. If you Google for my homepage, you can see links to all this cool stuff. So anyway, this is the Elementary Particle Explorer. It's a Flash application, so I'm sorry it won't run on your iPhone, but it would break it anyway. But it will run happily on your computer, and you can see all these different projections. And what's better is you can see how things interact. So once again, you can choose one of these particles, like this down quark, and then it'll highlight the particles you can interact with, like this gluon over here, and show that interaction. And it'll show you what you've clicked on, how it interacts, what all the twist numbers are around your 8 axes inside E8. And you can see that just doing the addition, you add minus 1/2 to 1, you get 1/2, that all the twist numbers add up for this interaction to happen. It's really very cool, but a very fun educational toy to play with.
How did it occur to you that it all fit into that?
Well, what actually happened is I had this, over 10 years, I tried to figure out how to get particle physics and gravity to play nice together geometrically. And I took the usual track, actually, of starting with gravity, it being the most well-understood force geometrically. And there's this trick of where you just add on other dimensions to gravity. It's called Kaluza-Klein theory. And you can do that to describe the other forces. The problem was I couldn't get the fermions to come out of that nicely. And I tried different ways, and I was trying to answer this question of what is spin within that context. And I couldn't come up with an answer to that. So usually, if when I spent like 5 years trying to do this, right? But but it wasn't working out, and I finally it came to admit to myself that it wasn't going to work out right. So I pitched it. Started working on the opposite approach, which is take the geometric description of particle forces using these Lie groups and expand that to include gravity. And that worked almost immediately. So what I found, and normally as a researcher you can't do that, right? Normally you have this bunch of literature you've built up, you have a bunch of graduate students, postdocs, everything. Over 5 years you get quite a bunch of momentum going in your academic career, which I didn't have. So I didn't have to worry. I could just wipe it all off my desk and start fresh, which I did. So working up from these Lie groups, I started with these Lie groups of the standard model, and you include gravity. And putting these together, I went back and found that what happens is you get the gravitational frame and the Higgs field for free when you do this unification of gravity with the standard model. And that this unification happens very nicely with the spin unification model. And that just seemed fantastic to me. And I got this bunch of algebra. So I had this algebra figured out for how gravity and the standard model and the fermions would all interact as a big bunch of math, right? And I'm looking at this bunch of math, and it's looking fairly consistent, right? It all seems to make this nice bunch of relationships between it. And so I was just had this crazy idea that maybe this bunch of math corresponds to a single Lie group. So I went looking. I tried some of the larger rotation groups, and then as a physicist, you don't see the exceptional groups. You're used to dealing with rotational groups all the time, but you don't see the exceptional groups very often as a physicist. But there they were, these other exceptional groups. And here's this big one. Well, it has enough space, it has enough pieces to fit. It has 248 sets of circles. So I tried to see if it would fit. And I looked on the internet, and I started reading about the structure of E8, the algebraic structure of E8. And sure enough, it was almost a perfect match. Okay, the standard model and gravity and one generation of fermions fit perfectly inside E8. And E8 had this enticing other structure relating 3 sets of 64 blocks of things that I might relate to the second and third generations. And I'm still trying to get that part to work. Until I can get that to work, I don't really have a complete theory. You can't really call this a theory of everything successfully until you get that part working. But I'm still working on that and trying to get that to work. But the fact that that worked, that I cobbled together this model first and then saw that it fit in E8, for me that was very compelling. That was a fantastic moment. And then, I turned the pages a few bit, except on the internet, of course, and I see that E8 has these weird diagrams describing its structure. And I look more deeply, and it's like each one of these diagrams, it turns out, mathematicians are calling these things roots. I'm learning representation theory over the course of a month, and I'm seeing that, wait a minute, these weights and eigenvalues that the mathematicians are describing, these are the charges. These are the charges of the physical particles with respect to different forces. And so that this abstract math is actually matching up perfectly with what we know for physics for these charges. And that was just fantastic. It was one of the most fun things I've been able to do as a physicist is be able to take the charges of the known elementary particles and match them up with the weights of the E8 root system and put that out as a paper with these great plots. It's fantastic. And it got more attention than I expected too, which is great. But yeah, basically, if you guys are dying for dinner or something like that, the talk is I've said all I wanted to say, and thank you all very much for coming. And but I'll have a bunch of questions.
Now the test.
Yeah. So
It's actually very easy. All we have to do is think in 8 dimensions.
that's all.
Thank you very much. Before we open for questions, and we don't have a microphone upstairs, is that right, Steph?
Right.
There are people upstairs too.
So you folks upstairs, make your way down here if you have some questions. Let me suggest to you that these are monthly meetings. We're not here to quench your thirst, but to perhaps provide you with some enticement for spicy subjects of intellectual curiosity at the limits of, at least for what we do here, at the limits of the science and technology that I think is growing on Maui. And we're very grateful to Garrett for providing us with quite a bit of spice.
Thank you, Jeff.
So,
Okay. Also, before people take off, I mean, I also want to say I live here on Maui. I'm here most of the time, so if you want to corner me in Whole Foods or Mana or something and talk to me about this stuff, that's fine too. Or you can follow me on Twitbook and figure out what I'm doing that way. That's a joke. You can friend me on Facebook or follow me on Twitter. But now I'll just hang out and answer questions and talk with you guys for a while.
Is there a schedule for the monthly?
So I should say, it's once a month. It's usually on a Friday towards the end of the month. There's a book sitting on the counter over here, a notebook. If you would leave your name and an email address, we'll put you on our list. We won't sell it to anybody, we promise, and we will send you an email notice when we have these talks.
Oh, also I forgot to I also forgot to say I recently wrote an article for Scientific American, and they sent me a box full of tear-out sheets for the article that I left on the counter there if you want to pick one up. But the lovely laser handling assistant is here, also sporting a EA T-shirt. Please go ahead and stand up and model. This is actually sold by an MIT student. The instructions are on the back. And this is actually sold by an MIT undergraduate physicist, but you can find links off my webpage or Google for it and find it. Okay, so yeah, questions, yeah?
So it actually seems like you're getting close to discovering the question to the answer of that thing and everything being 42.
I'm looking for that 42 every day, believe me. I'd really like that to happen. Yeah, but I think Douglas Adams, I'm a huge fan of Douglas Adams, and I think he was one of our greatest philosophers. So I think this answer 42 is a marvelous philosophical answer. I'm looking personally for a more mathematical and geometric answer.
I mean, like, what might that lead you to?
It's what makes this an exploration, right? Because I don't know where it's going to lead to, until I keep going. And really, like I said, I don't have a complete theory until I answer this question of what's going on with the second and third generations.
So,
Yes.
would you then, if this is the collection of stuff, would you then predict that there would just be 2 more generations of fermions and that's it?
Yes.
Okay, so no matter how high an energy you get in the accelerator, you just
That would be it.
stop.
No, if this unification is true about the universe, then E8 is a unique, very beautiful and unique structure. And if it is a true description of nature, you'd pretty much be done. I mean, this would be the final theory if it's true, because you're talking about 248 particles, and the symmetry would break down to what we have, and it would be very consistent, tight fit to nature if it can work out. That's a big if. Yeah.
Is there anything that might come out of the LHC that would help you? In other words, if as
Oh,
you
yeah.
go along, what kind of things might come out of there that would fit?
Well, what I want to see from the LHC is I want to see some sort of Higgs boson or mechanism that breaks electroweak symmetry breaking. After that, the next thing I'd most like to see is one of these X or Z prime bosons, which are these force particles that come out of unification. So when you have this unification in a larger Lie group, you have these other sets of circles that correspond to other force particles. And if they have just a little bit more mass than we've seen so far, the LHC might have enough energy to create these particles and these collisions such that we'd see them and see their effects. So that's the next thing I'd like to see after the Higgs, is something like a Z prime boson, something that has that's a force particle that's a new force corresponding to one of these unified models. After that, I'd like to see more Higgs particles, not just the minimal standard model Higgs particle, but also some colored Higgs particles that interact with according to colors, and have strong charges, and also interact non-trivially with these other particles. So I'd like to see sort of a richer Higgs sector in this way. So not just a simple Higgs come out of the LHC, but a sort of a cluster of interesting Higgs particles coming out all at once. This is the sort of thing I'd like to see come out of the LHC. And those are the top of my list. But like I said, I also had this menu of other X bosons and axions and these other particles, all the way up to this total of 248 that are in E8. I'd be very happy to see any of those. If the LHC sees particles that other people predict, such as superparticles, or maybe black holes that then evaporate, or something like that, due to higher dimensions existing other than the 4 of space-time that we know of, that would be bad for this theory, because those aren't on the E8 menu, right? All right. So I'm one of the, actually, the most highly anticipated particles for the LHC are probably superparticles. These are particles that are conjectured to exist that are partners to the known standard model particles that help balance them out theoretically. And I'd say probably, is it true? I'm not sure. It's around 50%. A lot of theorists vary wildly on what weights they give to predicting these particles. But a lot of people predict superparticles. And I've made several bets with other theoretical physicists about whether these superparticles will be seen against them, because I'm betting they're not going to be seen, and they're betting they are. So it's a great opportunity for betting. But there has to be a better way of making a living than making bets with Nobel laureates, but it's certainly fun. The LHC is running right now. They're ramping up to do more collisions. They're going to be running through I think 2012. And then after that, they're going to shut down for a year and do some repairs to their linkages between magnets so they can ramp up to even higher energies in 2014. So pretty much by the end of 2014, if things go according to plan, we'll reach some significantly higher energies with the LHC and be able to see a bunch of new particles. And by then, the end of 2014, we will have seen how the electroweak symmetry breaking is happening. And then we'll actually either see a Higgs or we'll see something like a Higgs by the end of 2014. That's the timescale we're looking at. But it might happen sooner. I mean, it's possible it could happen not tomorrow because they're not colliding the beams right now. They're just running them. But they might be colliding them tomorrow. That is going to be happening. So yeah, it's soon. But by 2014, we'll definitely see some new particles. Yeah, it is cool because we're going to get to see the rest of this pattern. And whether this matches this E8 or not, remember, I didn't start introducing the weird ideas until I started talking about unification. The rest of this pattern is a very accurate description of what we already know. And if all you want to deal with is standard models, you can just pick standard model here and just deal with the particles we know of and see those patterns. We already know it's quite pretty. Yeah, there was a hand that came up quickly.
Yeah, your table of Lie groups that you showed on one side, there's only 5 with the exception of...
That's right. Yep.
E8 is the biggest.
And E8's the biggest. That's right.
It better work because there's nothing else.
Exactly. If you really like Lie groups, then that answer is true. If you are into more elaborate models such as string and membrane models and other things, then you can build anything you want. Right?
Well, that was my next question. You use the term fiber. Is there
Yes.
a relation between fibers and string?
Not a direct relationship, although you can, differential geometry is probably flexible enough that you can probably, in some sense, describes a lot of string theory in terms of fiber bundles. But people don't do it that way. And this picture of a fiber bundle, when you're dealing just with one Lie group, that's a much cleaner geometric structure because you just have the 4-dimensional base of space-time and this single Lie group twisting over every point of this space-time. And that forms one space called the entire space of this fiber bundle. And if you just have a Lie group attached to this space manifold like this, this is an even nicer structure called a principal bundle. And you only have one field. So this is actually a unified field theory. If this is right, this is a unified field theory describing everything. That you have this, the unified field is this connection or superconnection field that describes how this Lie group is twisting over space-time. And elementary particles in space-time correspond to how this Lie group is twisting over those points of space-time as described by this superconnection field. So it's a very clean, very direct mathematical description of the universe in terms of geometry if it turns out to work right.
So you have these 8 dimensions, but it's still within the 4 dimensions of space-time. You don't need to add...
That's right. So remember, these 8 dimensions is just an abstract diagram for describing the structure of this Lie group. Technically, what you have as a full entire space is the 4-dimensional fabric of space-time. And that's only space and time because of how the Lie group breaks over it. So the gravitational frame is a direction inside E8 that via symmetry breaking imbues space and time with the space and time aspects. Otherwise, you just have a naked 4-dimensional manifold with no sense of distance or direction on it. But what you actually have as a geometry, as an entire space, is the 4-dimensional manifold of space-time and the 248 of E8 twisting over it. So you actually have a 252-dimensional entire space, which is enormous. But all we do is we move around in 4 dimensions, and we see these aspects of this higher dimensional Lie group space in our 4 dimensions of space-time manifested as the elementary particles that we see.
I was trying to understand if you showed like the standard group and the spin 3 models.
Yeah.
All the standard physics.
It's all standard physics, yes.
Where is the border between non-standard things and what you introduce?
Yes. So the non-standard thing is when I say this is all standard. Okay. The graphical depictions of this are all mathematically well established and known, but they're underutilized. So physicists weren't used to using these charge diagrams from mathematics to portray particle physics interactions. But even though I'm using this nice graphics to portray it, the physics and mathematics is all standard. Where it becomes non-standard is when I start just saying, hey, these might be part of this larger unified theory, which has a symmetry that breaks down to the other thing. That's more speculative. Because until you see the particles that correspond to that larger Lie group, you only have hints that this unification is happening. You don't know it's true. So until experiment verifies that this unification is happening, then you don't have reason to believe it. But once you've made the prediction that, hey, it might fit into this larger Lie group, which predicts these other particles, once you see a couple of them, that's enough evidence to say, hey, maybe this is actually happening. But we haven't seen any of them yet.
Why don't,
Right?
why don't we give people a chance to stand up, stretch your legs? The restrooms are over here.
Yeah.
And Garrett will be here for a bit more. Come on up and chat and ask.
That sounds great.
Thanks everyone again for coming.
Yeah.
I'm Connie. I met you at Jim's house some time back.
Oh, Jim, that's right. I do remember that evening. Connie, is that right?
Connie Giuliano.
Yeah.
Is there? You in a position at all to deal with the relative magnitudes of the forces themselves, the gravitation versus electromagnetic versus strong?
Well, if this in a unified theory, as you go to smaller distances, if this unification is correct, then they'd all have the same strength down at the smallest scale.
And what would those scales be? I mean, you saw
Down to zero.
But you get close, and and you say gravity would have the same strength
Yes.
as a strong force.
Yes. Yes.
Okay.
Yeah.
I like to. Okay. Thanks.
In really simplistic terms, I mean, is it basically all of these other elements that you're beginning to combine together are the output of the other blind men describing the elephant, and you're standing back and saying, wait a minute, if you put all these...
It's all part of this one
together,
E8 elephant.
You get an elephant.
Yeah, absolutely.
Okay.
Absolutely true.
Okay.
Excuse me. They were mentioning, you mentioned CERN and the Japanese, and I thought they found oscillating neutrinos in both places.
They do see neutrino oscillation, which means that... so that's one of the interesting things, is this SU5 model of unification doesn't naturally include the right-handed neutrinos, whereas spin 10 does. So in this 16 representation space that is very natural for spin 10, you have the right-handed neutrino components, which then allow you to have this neutrino oscillation and allow neutrinos to be described with mass. so that's good.
Yeah, I know. What happened was I postulated about 15 years ago that the universe oscillates. It's not a big bang. It just goes back and forth.
Well, people have had those oscillating cosmology models for
No, but it was
a while
Mel Schwartz who come up with the neutrino. We used to argue all the time. So nothing oscillates because they hadn't found any oscillations anywhere. But then they found the oscillations, and I talked with the head of theoretical physics, Pierre. No, he started up Pierre. He said, well, it seems like the neutrino is working at that level and this level.
Neutrinos could play a much more important role in cosmology than people give them credit to.
But you had a good point, because you've got the Higgs boson, and that question was, where is it?
Right.
And it's all energy.
Yeah, all these things do correspond to energy.
What happened to my theory is they say, well, it works, but then when and if they find a